A modern gaming PC already contains most of the building blocks needed for useful local artificial intelligence. The graphics processor supplies highly parallel compute, video memory holds active model data, and the CPU coordinates loading, tokenization, storage, and tasks that do not fit on the GPU. System memory provides overflow capacity. An SSD moves large model files quickly, and the power supply and cooling system support sustained operation. Converting the machine is therefore less about replacing its identity and more about configuring the hardware for a different workload. Gaming benchmarks and AI inference benchmarks measure different things. A game rewards fast frame rendering, driver optimization for specific engines, and stable latency. Local inference rewards memory capacity, memory bandwidth, supported compute formats, and software compatibility. A GPU that produces excellent frame rates can still be constrained by limited VRAM when loading a large language model. Conversely, a card that is no longer at the top of gaming charts may remain useful for smaller quantized models, embeddings, transcription, or image generation. Set realistic expectations. A single gaming PC can run private chat and coding assistants, summarize local documents, generate embeddings, support retrieval workflows, and experiment with vision or image models. It will not automatically match a large cloud cluster, train frontier models, or run every model at its maximum context length. The practical target is a dependable workstation that fits selected workloads, keeps sensitive data under local control, and produces acceptable speed without destabilizing the machine. The best conversion starts with measurement rather than shopping. Learn what the current system can run, establish a baseline, and identify the component that actually limits the desired task. That approach turns an existing gaming machine into an engineering platform instead of an endless upgrade project. Before installing software or ordering upgrades, create an accurate hardware inventory. Record the exact GPU model and its usable VRAM, not just the product family. VRAM often defines the largest model that can remain GPU resident, while GPU generation influences supported data types and acceleration features. Note the CPU model, generation, physical cores, and instruction support because model loading, prompt processing, and CPU fallback can place significant demand on it. Record installed system RAM, available memory slots, current module arrangement, and the motherboard maximum. System RAM must support the operating system, runtime, model loading, and any portion of the model that spills beyond VRAM. Inventory each SSD by interface, capacity, free space, and approximate speed. Model collections grow quickly, and insufficient free space can turn routine model updates into a maintenance problem. Inspect the motherboard for available PCI Express slots, lane sharing, physical clearance, storage connectors, and firmware support. Then verify the power supply model, rated wattage, age, connector availability, and quality. A wattage number by itself is not enough. A future GPU must be supported by the correct cables and safe sustained output. Review case dimensions, fan placement, dust buildup, and airflow from intake to exhaust. AI inference can hold components under load longer than a short gaming burst, revealing thermal limits that casual use never exposed. Finally, test the real machine. Check memory usage, temperatures, clocks, and power behavior under an existing workload. Consult manufacturer documentation before purchasing. An inventory converts vague assumptions into constraints: which models fit, which runtimes are supported, whether an upgrade is physically and electrically possible, and where money would produce a measurable improvement. The best operating system is the one that supports the hardware, runtime, and maintenance habits of the person using it. Windows is often the lowest friction path for a shared gaming and AI machine. Driver installation is familiar, consumer applications remain available, and tools such as LM Studio or Llama can provide a straightforward first experience. If the workstation must still function as the owner's gaming PC, preserving a stable Windows setup may be more valuable than adopting a technically elegant but unfamiliar environment. Linux offers deeper control over services, scripting, permissions, containers, and many machine learning toolchains. It is attractive for a dedicated workstation or a user comfortable diagnosing packages, drivers, and kernel interactions. That control has a maintenance cost. A Linux distribution, GPU driver, runtime, and model framework still need compatible versions, and an automatic update can disrupt a previously working stack if changes are not managed deliberately. Dual boot separates gaming and AI environments cleanly, but requires disk planning and a reboot to switch workloads. A separate AI installation on another SSD can reduce risk to the primary system. Windows Subsystem for Linux provides Linux tooling without a complete second operating system and works well for many development workflows, but GPU pass-through, networking, storage paths, and memory behavior add another layer to troubleshoot. Verify that the intended runtime officially supports the selected arrangement. Choose based on skill level and workload, then favor stability. Document driver and runtime versions, control update timing, and keep a recovery path. The operating system is not a performance trophy, it is the foundation that should make routine inference predictable, understandable, and supportable. Acceleration support determines whether local AI feels interactive or merely possible. NVIDIA hardware commonly uses CUDA, a mature compute platform supported by many AI runtimes. AMD workflows may use ROCm, where the operating system and GPU are supported, while Vulkan backends can provide broader cross-sender acceleration for compatible tools. Support varies by model, driver, runtime build, and operating system, so a GPU brand alone does not guarantee a working path. Think of the stack as a chain. The operating system recognizes the GPU through its driver. The runtime must be compiled for a compatible acceleration backend. That backend must support the GPU architecture and the numerical formats used by the model. If any link is incompatible, the application may fail to load, silently run on the CPU, or offload only part of the workload. Confirm acceleration through runtime logs and GPU utilization rather than assuming that installation success means the GPU is active. GPU offload places model layers or operations on the graphics processor while retaining the remainder in system memory and on the CPU. Full offload is usually faster when the model fits in VRAM. Partial offload can make a larger model usable, but data movement and CPU computation reduce speed. CPU-only inference remains a valuable fallback for troubleshooting, embeddings, and smaller models, though interactive generation is typically slower. Version discipline matters. Record the known good GPU driver, acceleration runtime, and application build. Do not update every layer at once. When a change is necessary, verify one representative model before modifying the rest of the environment. A slightly older stable stack that consistently uses acceleration is more useful than a newer combination whose compatibility has not been proven. Begin with one runtime that makes the first useful workload easy. LM Studio provides a desktop interface for discovering compatible models, adjusting settings, chatting, and exposing a local API. Llama emphasizes a simple command line and service workflow with packaged model definitions. Both can reduce setup friction and help confirm that the hardware and driver stack work before additional components are introduced. Llama.cpp is a foundational, highly portable inference project with extensive control over quantized models, CPU execution, and several GPU backends. It is useful when you need explicit tuning or want to understand the underlying inference options. OpenWebUI adds a browser-based conversation layer and can connect to backends such as Llama or compatible local API servers. Text Generation WebUI offers a broad set of loaders and controls, but its flexibility also creates more configuration choices. Select a tool because it supports a defined use case, not because it exposes the largest number of switches. Local API servers allow editors, scripts, retrieval systems, and other applications to call the model through a consistent interface. Start by binding the service to the loopback address so only the workstation can reach it. Test a single client, confirm authentication options if remote access is later required, and document the model name, port, context settings, and startup method. Avoid unnecessary orchestration during the first pass. Multiple front ends, containers, proxy layers, and model servers make failures harder to isolate. Establish a simple path from model file to successful accelerated response. Once that path is measured and repeatable, add interfaces or automation one component at a time. Simplicity at the beginning is not a limitation, it is a controlled baseline for everything that follows. Model selection is a resource matching exercise. Parameter count provides a rough indication of model size, but the loaded footprint also depends on numerical precision, quantization, context length, and runtime overhead. A model that nearly fills VRAM before receiving a prompt may run out of memory as its context cache grows. Leave operating margin instead of treating published file size as the complete requirement. Quantization reduces the precision used to store model weights, lowering memory demand and often increasing speed. The trade-off can include some loss of output quality, especially at very aggressive settings. A well-chosen quantized model that remains on the GPU often produces a better interactive experience than a larger model split heavily across slower system memory. Test more than one quantization when quality matters, using prompts that reflect the real task. Choose the model family for the workload. General chat models are useful for drafting, explanation, and summarization. Coding models prioritize software tasks. Vision language models accept images but require additional memory and compatible runtime support. Embedding models convert text into vectors for search and retrieval. They are usually smaller and should be selective for language, retrieval quality, and application compatibility. Do not assume one model must perform every role. Context length controls how much text the model can consider, but larger settings consume memory and can slow prompt processing. Set context to what the workflow actually needs. Begin with a smaller, well-supported model that runs reliably, record speed, and memory use, and evaluate answer quality against representative tasks. Scale upward only when the smaller model fails a meaningful requirement. A stable model that fits the workstation and consistently completes the job is the right model, regardless of leaderboard fashion. Performance tuning begins with a repeatable workload. Record the model, quantization, prompt, context setting, runtime version, and acceleration backend. Then measure time to first token, prompt processing speed, generation tokens per second, and total completion time. Tokens per second describes generation throughput, but it does not capture a long delay while the prompt is processed. Both measurements affect whether a coding assistant or chat interface feels responsive. Watch GPU utilization and VRAM allocation while the request runs. Low GPU activity may indicate CPU execution, insufficient offload, or a workload that is waiting elsewhere. VRAM near its limit can produce allocation failures or force compromises in context size. Monitor system RAM and storage activity as well. Heavy swapping can make a configuration technically functional, but operationally unusable. Thermals, fan noise, and power draw matter during sustained use. Observe temperatures and clock speeds over a long session, not only during startup. Falling clocks combined with rising temperature indicate thermal throttling. Sudden shutdowns or instability may point to power, cabling, overclocking, or cooling problems. Prefer a stable power profile over a marginal performance gain that increases heat and noise substantially. Change one setting at a time. GPU offload, batch size, context length, and runtime-specific cache options can improve one phase while worsening another or increasing memory use. Keep a small benchmark table and compare results against the real workload. The objective is not the highest isolated number. It is predictable latency, adequate output quality, and sustained operation within the machine's thermal and memory limits. Local operation can improve privacy, but local does not automatically mean secure. Model files, runtime packages, extensions, and installers are software supply chain inputs. Obtain them from reputable sources, verify hashes or signatures when available, review license and provenance information, and avoid executing unfamiliar model packages that require custom code. Keep an inventory so an affected component can be identified when a security advisory appears. Treat a local AI API like any other service. Bind it to the loopback interface unless another system genuinely needs access. If network access is required, use host firewall rules, authentication, encryption, and a limited trusted network. Do not expose an unauthenticated inference endpoint directly to the internet. An attacker could consume compute resources, access connected data sources, or use the service as an entry point into the workstation. Separate users and workloads where practical. Protect sensitive prompts, retrieve documents, chat histories, API keys, and logs with appropriate file permissions and storage controls. Understand which applications retain conversations and whether telemetry leaves the machine. A model can reproduce sensitive material supplied in its context, so local processing does not remove the need for data handling rules. Reliability is part of security. Backup configuration files and important data, but avoid backing up huge model collections blindly when they can be re-downloaded. Record known good versions and export settings before major changes. Apply operating system, driver, runtime, and interface patches deliberately, then test a representative workflow. A stable configuration snapshot and a rollback plan allow experimentation without turning every update into a recovery exercise. A gaming PC becomes a capable AI workstation through deliberate configuration, not through a single installation or expensive upgrade. Begin with an exact inventory of the GPU, VRAM, CPU, system RAM, storage, motherboard, power supply, and cooling. Those facts establish the machine's operating envelope and prevent model or hardware choices based on assumptions. Select an operating system that you can maintain and that supports the intended acceleration path. Treat GPU drivers, CUDA, ROCm, Vulkan, and the selected runtime as a compatibility chain. Prove that acceleration is active with a simple setup before adding interfaces and orchestration. Then choose models by workload and available memory. Quantization, context length, and partial offload are engineering trade-offs, not magic ways to erase resource limits. Measure real tasks. Generation speed, prompt processing, GPU utilization, VRAM, system RAM, temperature, power, and noise together describe the user experience. Change one variable at a time and preserve a known good baseline. Upgrade only when evidence identifies a clear bottleneck and the proposed part can be supported by the case, motherboard, power supply, and cooling system. Finally, protect the workstation. Use trusted model and software sources, restrict API exposure, control sensitive prompts and logs, patch deliberately, and keep configuration backups. The goal is not to run the biggest available model or assemble the most complicated stack. The goal is reliable, private local AI that serves a defined workload, remains understandable to its operator, and can be recovered when something changes.